So we continue with the program, and next talks by Paul Emmerich, who's presenting Moongen, scriptable high-speed packet generator, its design and implementation.
Hi, I'm going to talk about my packet generator, which is written mostly in Lua, and it does some quite amazing things thanks to Lua. If you want to learn more about the packet generator, I also have a second talk tomorrow in the SDN dev room. This talk focuses on kind of unique challenges we had when using Lua for a really high performance thing, and also comes with some challenges like multi-threading, optimizing stuff, integrating C, just to name a few. If you want to learn more about how to use it or why you would even want it, then the SDN dev room tomorrow at noon is the second talk. So what's a packet generator? Well, this is a packet generator. This is a large box. You can buy them from some hardware vendors. They are usually really expensive. This box is tens of thousands of euros up to above 100,000 euros. Well, what it does, it tests networks. You put in your Ethernet cable and then it sends out lots of packets. And by lots of packets, I mean you can put in there multiple 10 gigabit or 100 gigabit cables in this thing, and it completely fills them with small packets, which is quite challenging to do. So obviously, I'm working at the university. We do have some funding, but not enough to spend 100,000 euros on a packet generator. So we were looking into how can we do the same thing in software. And I've been using quite a lot of packet generators in software, and they were either slow or unusable, or both slow and unusable. So I thought, well, can't we do this better? And yeah, we can. And I designed Moongen, which is a packet generator written almost entirely in Lua. Why Lua? Well, because it's fast, and by writing everything in Lua, I get a really huge flexibility. If you use a typical packet generator in software, there's either a complicated configuration that makes no sense or is hard to adjust to your specific use case or hard to extend to new protocols. So I really didn't want that. So what I wanted was, the main goal was flexibility and speed. So I opted to just generate all the packets in Lua code. That means if you want to send a specific type of packet with Moongen, you write code that generates that packet and send it out in real time. It's obviously cheaper than a hardware box from the previous slide. You can get a software system with some 10 gigabit ports for 1,000 euros or something. 10 gigabit network cards are nowadays in the range of a few hundred euros. So quite affordable compared to hardware packet generators. So it's obviously more flexible than a hardware box, because you can easily extend it to new protocols. You can just implement the protocol in Lua and then run it, and it does whatever you wanted it to do. So how are we achieving the flexibility? The speed? Well, obviously LuaJIT. Then the framework DPDK. DPDK is a framework by Intel, which is, well, the simplified version. It's an optimized set of drivers. Because you can't just use a normal operating system interface if you want to send test traffic at rates of millions of packets per second. It just doesn't work if you need to do too many syscalls. So the DPDK framework, really nice. Then we do explicit multicore support in all of our API. Everything you write is multicore aware, and I will come to that in a second, because doing multi-threading in Lua is not something that you usually do. Flexibility, as I already mentioned, all packets that are sent out are crafted in real time in a user-defined Lua script. So you write a script instead of a configuration file, which works really well. Then another key feature is precise timestamping. We did it by misusing some hardware features found on some server commodity NICs, and then we wrote a simple driver that sets some magic registers to the right magic values, and then you get precise latency measurements, which is something that all other software packet generators fail to do. So how do we do multi-threading? So you probably know, well, some of you probably know some libraries for Lua that claim to do multi-threading, or some of you Googled them once. And yeah, there are some libraries, but they well, not that well maintained, most of them, and most of them also do not really map to our problem domain that we have. So what we did a simple brute force solution. We just start multiple independent Lua JIT virtual machines. So basically multiple Lua states, and each one gets pinned to a separate thread and a separate CPU core, and then you have multi-threading. Of course, the obvious disadvantage is you now have no shared state between the Lua farms. But it turns out that we, for our use case, don't actually need shared state. Because we are generating test traffic, and there are typically different types of flows. Let's just say you're testing some box which does some quality of service feature. Then you send one traffic that is to be a high priority traffic, one low priority traffic, and that's something that's completely independent. Each of them can be tested independently. So you have two threads, and they basically do the same thing, just with different traffic types. And that works really well. The second thing is that these modern network cards, if you buy a network card, they are actually natively multi-core aware. That means you can use them as multiple independent cards. And what the network cards do, of course, traffic you send to the network, they just mix it all together. And receiving traffic, you can configure filters and tell them traffic that matches this filters goes to this queue, what it's called, or you can distribute the traffic based on a hash function on the network card, and then you can use each of these queues on the network card independent from each other. We just map one queue to one Lua JIT VM to one CPU core, which works really well. We of course need some communication between the threads, but that's only for low priority data. Basically, like threads report their current statistics, the throughput they are seeing, the latencies they are measuring at the moment. But that can be slow, so we wrote some low-level C functions that just basically do simple message passing API. We use the excellent library Serpent for the serialization, and so we can pass around arbitrary Lua objects across threads. It's kind of slow, and when I say slow, I mean in the order of 100,000 messages per second, depending on the complexity of the object. The serialization is really the bottleneck here. But that's okay for statistics. It wouldn't be okay for packets where we are aiming for millions of packets per second. What does it all look like? Well, we have three layers. On the bottom, we have the hardware, which is multi-threading aware with multiple queues. Then we have the DPDK library, which is a low-level abstraction interface. And what it does, it offers APIs for configuration of the hardware and APIs for pushing packets or receiving packets from the API. Then Moongen core, at its core, Moongen is simplified just a wrapper for DPDK. Well, it's not just a wrapper because we offer a lot of utility functions and all the multi-threading and so on. And on the very top is what we call the user script. The special part about this is that the user actually writes the entire logic of the packet generator. Of course, Moongen comes with example scripts to do that and whatever. But the idea is you take one of these example scripts which matches or kind of matches the test you're trying to do, and then you modify it to your needs or add whatever, or copy and paste from different example scripts together, or reuse modules. And of course, all usable modules are implemented in some utility libraries like timestamping or protocols and so on. So what does it look like? For example, if we want to generate some UDP packets, then you would write code like this, which I think is way nicer than a configuration because it's easily extensible. And all other packet generators I've used, at some time I had to touch the source code just to get them to do what I wanted them to do. And yeah, one of the reasons why I just said, okay, I'm touching the source code of all the packet generators used anyways. So why not let the user write the source code? Okay, what this code is doing, it's quite simple. First thing is we create a memory pool. Memory pool is just an area for buffers that can be efficiently passed to the network cards. We initialize in the callback function all the buffers with some default value. In this case, some default UDP values. You can pass an argument to the fill function, as you will see later. But here, for space reasons, just some default values. And then we send them out in the main loop below. The main loop does just in line 7, it allocs some buffers. The size, the 60 here, is not actually the number of buffers, but the size of each packet we are sending. 60 is the minimum size that's legal on an Ethernet network. And then what we are doing, we are looping over all the buffers we just allocated, and then we can say, okay, this buffer is an UDP packet. The get UDP packet function is just a fancy way to do a cast to some C struct, which then is an UDP packet. And then you can access the packet like it was an UDP packet and tell it like, yeah, we want to randomize the IP source address, and we also want to randomize the UDP source port. And then we just tell our library to enable checksum offloading, which just sets some flags, and then the network card calculates all the checksums, and then we can send out the buffs on a queue. And as you can see, this function, you can, as one of the, in the previous slides, one of the slave scripts in the top right, and you could start this function multiple times in multiple independent LuaJIT VMs and pass it different types of parameters. In the simplest case, different queues, and then you just generated traffic natively for multiple cores at the same time. But you could also pass other parameters to it, like the range to randomize or which ports to use or anything else. You can check out our GitHub repository. There are a lot of example scripts for various use cases. So how is this packet data stuff working? One important challenge for packet generators is that they are written for testing stuff. And from testing, you often test new protocols or weird edge cases. So that's where a lot of configurations actually fail or not implement the latest protocols. So we have almost endless number of different protocols, and then a literally endless number of combinations of these protocols, because you can stack tunnels into tunnels and whatever. Yeah, and what we need to have in the packet generator, especially as we are building all packets in real time as they are sent out, we need efficient access to all these protocol headers from script code, and we want these accessors or the underlying packet, we want it to have in the right data structure. So we don't want to copy the packet at any time. We want to build the whole buffer in Lua and then just pass it to the driver and send it out. So what we did is a kind of dynamic approach. We have this create packet magic function, which actually is in a namespace but omitted here. So what it does, it takes a few protocols. The protocols are defined in modules. So if you implement a new protocol, you add your module there. The protocol basically represents the header of that protocol, and create packet just takes multiple protocols and stacks them together. In this case, we are having an Ethernet on the lowest layer. Then we have an IP above that. Then we have UDP. Then we have VXLAN. VXLAN is a tunneling protocol. So we have another Ethernet header and another IP layer. And this weird syntax with the tables here, it's just because we need to rename them. As you can see in the next line, we can access the packet after we use the function returned here is a cast, which turns the buff into a cast the buff to such a packet, and then we can do all the required magic here. Yeah, all these setter functions are defined by the protocols, and they handle stuff like endianness swapping, because usually the network byte order is not your host byte order, and it's all handled by the class that is created dynamically. This is extremely fast, and that is thanks to a LuaJIT FFI, and it's really, I've benchmarked where it's even faster than C packet generators written in C. Basically, the main reason for it being faster is that these packet generators need a huge switch statement in their main loop, basically, which tells, is this configured? No, then we need to do this, and etc. With this LuaJIT approach, you just write your really, really small main loop, which does just the actions you really need. And yeah, these calls to set whatever, you obviously wouldn't use the string thing here. The function also accepts a pre-passed number, and you can do a pass IP address, and then you get an opaque object which you can pass to, stuff like this. Yeah, that's really fast, these accessors. Then the memory layout is defined by the C data struct, so we can just send out the packet immediately after we created it. No additional copy step necessary. It's just something. I also looked at other stuff when I designed Moongen, like the V8 API, where stuff like this is way more complicated. Okay, to give a quick summary, what we are doing is we use user scripts instead of some complex configuration. Then LuaJIT is fast, really fast. And if I mean fast, I'm saying more than 50 million packets per second per CPU core. I've successfully tested this with up to 100 gigabit Ethernet, and it works on these high speeds. Of course, you need 10 CPU cores to do that, but yeah. This is something other packet generators fail to do. And then, despite this high speed, we run a script code for each single packet we send out. Just a simple calculation. We are doing 15 million packets per second, which is 10 gigabit with minimum size packets. Your CPU, let's just say, has 3 gigahertz. That means you have 200 cycles per packet. And all this includes the Lua calls to modify header fields, calls to random or whatever. We can send out a completely random packet, or we can touch all header fields and send out a packet and use less than 200 clock cycles per packet. I think that's quite impressive, thanks to LuaJIT. And yeah, we make heavy use of the LuaJIT FFI and C libraries like DPDK for low-level stuff. We, for example, all the drivers we use are the DPDK drivers, and they are just LuaJIT FFI wrappers. If you want to, one could write the drivers in Lua. I don't know if anyone of you is aware of the SnapSwitch project. They are doing exactly that. They are writing the drivers in Lua, which I think is kind of crazy. And I was thinking about using these Lua drivers from them, but then I decided for DPDK because it's slightly faster and has better multi-core support. So that's basically it. I'm open for questions, and you can check out everything on GitHub. Yeah.
Could you go back to the slide before this one?
This one?
Yeah.
Yeah.
Does this you say create packet there?
Yeah, the
for packets you receive too, so you can
okay.
inspect them and modify them.
Create packet is actually misnamed. It should actually be called create protocol stack wrapper or something. But yes, you can apply it on received packets. Receiving packets also fully featured, but not something we usually do. In the end, this is just a C data struct, and this is just a wrapper around a FFI.cast. So yes, and there are also there's also a function which looks at an incoming packet and determines what protocol it is, and then automatically does this for you and gives you whatever you need. I think there's some example code that does receiving packets. I think quality of service test.lua is what you want to look at. It receives packets and checks the UDP port to compare different flows. Yes?
You're saying you're using C for the drivers. So do I understand you right that you're not communicating with the kernel, letting the kernel do that? Or?
No, the kernel is too slow for high-speed networking. DPDK is a library which just maps the whole PCI, the relevant PCI devices and their DMA space into a user space process. So what we're also doing is there are some parts of the code which directly access PCI registers from Lua code.
So there are probably a lot of cards that are not supported.
Yes, almost all 10 gigabit cards are supported. Gigabit cards are a little bit more tricky because they are often old and annoying. I sometimes get requests from people, I want to test this gigabit card. I often have to tell them, please buy this 10 gigabit card because it's better even for gigabit speeds. Other than that, yeah, it's up to the DPDK library what they support.
Will it be hard to port drivers to myself from, for example,
It's not usually something you want to do. These drivers are, well, I mean, they share a lot of code with their with their kernel space companions, but I think the 10 gigabit drivers are in the range of 20,000 lines of code in DPDK.
I think we're out of time actually, so
I'll be there after for